9, resume your own navigation, direct to Daventry, contact London 133.45.
Approaching the millennium, there's no let up in the demand for air travel. But in Europe's busy skies, there are limits to the scope for increasing airspace capacity using existing methods and technologies. The limiting factor is usually the workload on individual air traffic controllers. This workload must be kept within safe levels. Today, researchers across Europe are in partnership to develop new systems and technologies to allow more aircraft to be handled while maintaining the commitment to safety and keeping the workload of both pilots and controllers at acceptable levels. These developments should ensure that tomorrow's system can handle the projected increase in demand. PHARE, the Programme for Harmonised Air Traffic Management Research in Eurocontrol, is a collaborative research and development programme managed by the Eurocontrol Agency and involving 5 European partners. The Centre d'Etudes de la Navigation Aérienne, or CENA of France, the Deutsche Forschungsanstalt für Luft- und Raumfahrt, or DLR of Germany, the Eurocontrol Experimental Centre at Bretigny near Paris, the National Lucht- und Ruimtevaart Laboratorium, or NLR, from the Netherlands, and the United Kingdom National Air Traffic Services Limited, or NATS. There are 3 main elements to the PHARE programme. First, the partners are developing and testing new aircraft navigation and 4-dimensional flight management systems which can predict an aircraft's future trajectory in both space and time, and accurately fly that trajectory. Second, the partners are looking at computing systems which can provide automatic assistance to controllers to help them resolve potential conflicts and to plan the best use of the airspace. Third, they're examining the use of systems that can ease both controller and pilot communications workload, and which make possible the sharing of data by ground and airborne systems. As well as testing and evaluating these developments, the PHARE partners are performing a series of realistic simulations to evaluate the performance of the integrated air-to-ground air traffic management system. The first of these major demonstrations, PHARE Demonstration 1, or PD1, was hosted by NATS, the UK Defence Research Agency's Malvern establishment. PD1 simulated en route airspace based on air traffic flows predicted for the year 2005. The demonstration investigated and evaluated the changes in traffic throughput and controller workload resulting from the new systems, and assessed pilot and controller reaction to the changes involved. As with all the PHARE developments, PD1 was directed by the PHARE Management Board and at the technical level by the PHARE Coordinating Committee. Work started on PD1 in 1992 by specifying the operational scenarios for the demonstration, agreeing the types of computer tools to be tested, and identifying the system facilities that would be required. The next stage involved modifying the NATS research facility, which is a network of sophisticated computer workstations for use in the UK trials programme, by integrating software and hardware modules developed by the PHARE partners. These are 4 advanced computer assistance tools: a trajectory predictor, which accurately predicts an aircraft's future trajectory in space and time; a conflict probe, which detects possible conflicts between trajectories; a problem solver, to help the controller resolve conflicts; and a flight path monitor, which alerts the controller when an aircraft deviates significantly from its agreed trajectory. In addition, a new man-machine interface designed to enable the controller to interact with the new tools and operational procedures. An experimental 4-dimensional flight management system which was installed in the NATS-funded UK Defence Research Agency's BAC-111 aircraft. And a data link, the NATS Mode S data link, to enable two-way communication between the air and ground systems. Together, the aircraft and ground systems form an integrated air traffic management system which offers the prospect of a major advance in system performance. It is, of course, vital to measure the effect on performance of the introduction of both the new computer assistance tools and data-linked aircraft equipped with the four-dimensional flight management system. Therefore, a reference system, which is similar to present-day operations, was developed. There were 3 stages of demonstration trials, which PHARE called organizations, with progressively greater use of computer assistance and data link facilities. Organization 0 was the reference system. Organization 1 used the reference system and the new PHARE computer assistance tools. And Organization 2 used the reference system, the new PHARE computer assistance tools, the experimental flight management system, and the automatic exchange of information between the aircraft and the ground. These systems were assembled at Malvern using software and hardware modules supplied by the PHARE partners. Only when integration tests and pilot trials were successfully completed were the main PD-1 trials held in the second half of 1995. PD-1 was based on the planned UK sectors 10 and 11, which cover en route airspace between the Netherlands and England, and used feeder sectors to control traffic in and out of adjacent en route and terminal area sectors. As with many current systems, PD-1 used 2 controllers per sector, a tactical position focusing on the radar picture, and a planning position mainly concerned with flows in and out of the sector. To provide realistic air traffic, a multi-aircraft computer simulator was used to generate simulated aircraft, which fly according to data derived from the air traffic control instructions from the 4 controllers at their experimental workstations. The PHARE concept starts with the pilot proposing a trajectory from departure to destination airport. If the trajectory is safe, the aircraft is permitted to fly it. But if there are potential conflicts, the ground system controller applies the necessary constraints to the trajectory to ensure safety. During the trial, an aircraft trajectory was generated from information entered by the pilot either on startup or while airborne. The trajectory was optimized using aircraft speeds and climb rates that maximize fuel efficiency for the particular aircraft type. Once generated, the trajectory was passed via the air-ground data link to the ground system, where the conflict probe checked for potential conflicts with the trajectories of other aircraft. If potential conflicts were identified, the planning controller used the problem solver to modify the trajectory so that it was conflict-free and to ensure safe separation. The modified trajectory was then sent to the aircraft as a set of 4-dimensional constraints or restrictions on the airspace which the aircraft could occupy at a given time. The aircraft system then determined the most efficient trajectory using these constraints. When the pilot accepted the trajectory, it was data linked back to the ground. If not accepted, the pilot proposed a new trajectory, and the process was repeated. Once the process was complete, the aircraft's position in relation to its agreed trajectory was monitored by the aircraft's flight management system, and on the ground by the flight path monitor. Because the trajectory is 4-dimensional, the space in which the aircraft is required to fly is defined as a bubble. Not all aircraft will have a data link capability within the time frame modelled in the demonstration. For these aircraft, the planning controller used a ground system trajectory predictor to generate the most economical conflict-free trajectory based on data stored in the ground computer systems for that aircraft type. The ground system then produced advisory messages for the tactical controller. These were relayed verbally to the pilot so that the aircraft followed the agreed trajectory. These manual procedures involve more work by controller and pilot, and so were less efficient than one where trajectory information was automatically data linked to the aircraft system as in Organisation 2.
Finnair 960, climb to flight level 280.
Climbing to 280, Finnair 960.
The main PD-1 trials were made up of a comprehensive series of hour-long runs, during which the systems corresponding to all 3 organisations were used. There were 8 weeks of trials using the 3 different organisations and a range of air traffic volumes. Runs on Organisation 2 used an increasing proportion of aircraft equipped with the 4-dimensional flight management system. Some of these runs included the BAC-111 experimental aircraft. Different controllers were used for each week of the trials. These controllers were drawn primarily from a range of European air traffic control organisations. Some Canadian controllers also participated in the trials. To ensure their familiarity with the systems under evaluation, controllers received extensive training, which involved briefings, sessions on standalone training simulators, and runs on the full system. As has already been stressed, measurement and analysis formed an essential part of PD1. This was overseen by the PHARE Validation and Tools Group. Large amounts of valuable data were recorded during the trials using several different measurement techniques. For example, quantitative data was stored by the computer system and were analysed to give information on throughput, delays, and the number of aircraft handled in a given time period. Measures of perceived controller workload were recorded. Controller communications and input activities such as keystrokes and mouse or trackball operations were monitored using audio and video facilities. And a combination of questionnaires and debriefs were used after each experiment to find out controllers' perceptions of the system and pick up suggestions for improvements. The extensive data collected during the demonstration require full analysis, and considerable effort is being expended on this important part of the demonstration. The initial analysis, following the main evaluation phase, is expected to last up to 6 months, with more detailed analysis continuing throughout 1996. Preliminary investigations already indicate that the introduction of the new tools brings benefits to the controller's operating procedures. Measures of the controller's communication workload, for example, derived from audio recordings made during the trials, indicate an overall decrease in workload, with the introduction of the new tools corresponding to organisations 1 and 2. The potential benefits would be seen by the customer. For example, the results shown here indicate that the amount of time the aircraft spent at their cruise flight level increased as the new tools were introduced. The interpretation of other results is less straightforward. Examination of perceived controller workload indicates that more work is yet to be accomplished in both refining the computer assistance tools and in training the controllers to operate the advanced PHARE concepts. An important factor in evaluating the new systems has therefore been the reaction of controllers to the system, an investigation of the factors influencing their perceived workload. The debriefs revealed that the majority of the controllers approved of the windowing environment used in PD1, and in particular the data presentation with its absence of electronic or paper flight strips and the mouse cursor interaction. The concept of the computer assistance tools and the four-dimensional data link trajectory exchange were also generally welcomed, although an early result is the need to do more work on the role of the tactical controller. This is because some tactical controllers consider themselves to be under-involved in the control strategy, making it difficult for them to maintain a mental picture of the airspace under their control. The analysis performed so far has only provided the first insight into the effects of the introduction of some of the new computer assistance tools. Large quantities of numerical, video and audio data are now being analysed. Although there are already indications that a reassessment of current flight patterns to include concepts such as direct and oceanic routing may be beneficial, further insight into the best way of using the new computer assistance tools should be gained as the analysis continues. By demonstrating the feasibility and merits of the PHARE concept, using a limited range of advanced computer assistance tools, four-dimensional flight management systems, and data links in the en route environment, PD1 has successfully laid sound foundations for the future PHARE demonstrations. These future demonstrations will extend the assessment to tools for arriving flights in the terminal control area around airports, and then for both en route and terminal control area tools in a full-scale integrated trial. In this way, PD1 is preparing the way for a complete air traffic management system, one that will be capable of supporting the growing needs of air passengers well into the next century. PHARE is now truly en route for the future.